Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah. So we meet again. So in part 3, beam analysis using stiffness matrix method. So what we are going to do tonight is to actually review. I want to review your submission, okay, regarding question I have given to you this morning, and after that we will try to draw the shear force diagram as well as member of bending moment diagram, shear force and bending moment diagram. Okay, where is it? Wait. Okay. Okay, I got some submission here, 12 responses, and this is what I received. Okay, okay, let's look at one here, submitted by Nurul submitted by Nurul Amirah. Okay, let's go through this together. Okay, so as usual, if we have beam question using stiffness beam question or thrust question, okay, basically the procedure or the question just look like the procedure, the question. Okay, number one, we have to establish element global stiffness matrices. Okay, number two, from the element global stiffness matrices, we will produce the structure stiffness matrix. And the structure stiffness matrix. Okay, the structure stiffness matrix, okay, global element, stiffness, the symbol is K. Stiffness, the symbol is K, that is stiffness. Okay, worldwide, known stiffness as K. Okay, the stiffness. Okay, so for element stiffness matrices, we use label K1 and K2. K1 and K2. So this the answer for A, we label as K1 and K2 for the element global stiffness matrices. Okay, K1 and K2. Since we have member AB and member BC, there are two members only, two element, K1 and K2. Okay, so typo here, this is capital K, capital K, and when we combine K1 plus K2, K1 plus K2, we get K capital. So basically, we will use capital letter for the whole, for the structure, for the whole, and we use small letter for the element. Same goes to Q as well. When we do it for the whole system, the structure, we use capital letter. When we calculate for the element, so we use the label, the small letter for the label. Okay, and after that, from stiffness matrix, from stiffness matrix, we we will produce the stiffness equation. Okay, stiffness equation, because we can only solve the displacement, the unknown displacement and unknown reaction using stiffness equation. So even though in the question there is no question asking about writing the stiffness equation or force displacement equation, so that step is compulsory. Okay, even though you don't have to write in full, but you have to have that in order to solve for the unknown displacement. Okay, so calculate unknown displacement using stiffness equation. And stiffness equation for beam, is Q is equal to KD plus Q naught. Q is equal to KD plus Q naught. Okay, Q naught is equivalent nodal forces. Equivalent nodal forces, we calculate the value from element. So we will have small q, then combine to have capital Q naught. Okay, so this is the equation for beam, because beam normally the member will be subjected by loading UDL on the member or point load on the member. That is why we use this. Okay, this equation, when previously we analyzed thrust, we just consider Q is equal to KD. Q is equal to KD because thrust has no UDL, has no point load at the center of the member. So basically loading is given directly to the nodes in thrust system. That is why we only use Q is equal to KD. However, this equation, Q is equal to KD plus Q naught, Q naught is also exists in thrust whenever the thrust has the effect of temperature changes and fabrication error. Okay, so that example we will cover in another video. Okay, another lecture session. Okay, so when we solve this, we get unknown displacement, and we will calculate after that unknown reaction using displacement that we calculated. Okay, and after that we put all the value into the diagram, and then we can start draw the diagram, the shear force diagram and bending moment diagram. So from this, okay, when we label, we have to label according to unconstrained and constrained system. Unconstrained and constrained system, you just need to sketch. So we label start from constraint, start from constraint, because at constraint there are unknown reaction. Okay, from support we can identify unknown reaction. So we have two pin support here, two pin support, but we only count 2 degree of freedom because we don't have to count x. So that we don't have to count AX, we don't have to count CX. So we only count 2 in Y and Z component. Y and Z component. So that's why we put 2 at A, 2 at B, 2 at C, 2 at A, 2 at C. So 4. There are 4 degree of freedom in constraint system. So since there are A, B, C, 3 nodes, 3 join, so in total there are 6. So remaining 2 we have to put at B in unconstrained system. In unconstrained system. So when we label, we will label start from unconstrained. 1. We label 1 start from constraint. So this one correct. This one YZ 1 2. So YZ 3 4, YZ 5 6. Correct Correct. Okay. Then so we transfer all this label into the main diagram. So we will get member AB or K1 or element number 1. The label will be 3 4 1 2. So this is correct. 3 4 1 2, this is correct. Okay, 3 4 1 2, 3 4 1 2. Okay. After that we have to use formula. So normally when we establish K for element K1, if element has 2 EI, so we will times the value that we get with 2. So we just put EI outside. Okay, because we want to plus K1 and K2, so just EI. We just put EI outside the matrix. Okay, so we will compare this answer with the next student. Okay, don't worry if, for the label is correct. So the answer we will compare with the next student. Okay, you just need to calculate based on the formula given. Okay, so for K2 is 1256. 1256. You must follow the direction, this direction, because this is the sign convention. The formula that is the formula of K derived based on this assumption. Y upward, Z counterclockwise, means that you cannot change direction. You have to follow this direction. Okay, so K1 the label 3412 and K2 1256. Okay, 1 2 we only have EI, right? EI. So I believe this the answer in the bracket is correct. So this is 1256. Okay, so this label shows the position in the structure stiffness matrix. The structure stiffness matrix, It must be written in order later on. Okay. Next is because the label that we will use in equivalent element nodal forces is also same with what we label in K1 and K2. So that's why, okay, we can calculate this directly after we calculate K. Okay, doesn't matter if you want to plus K1 plus K2 to get total K, also okay, or you want to calculate equivalent forces right now, also okay. Okay, so equivalent nodal forces, the label is capital Q naught. Okay, for element is small q. Small q, okay, this is Q naught, Q1 naught or Q naught 1, doesn't matter. Okay, so it will follow label, the same label that we use in K. So for Q1, Q1 naught, so we will use the same label. This label 3412, 3412. So this must also 3412, 3412. And for Q2 naught, okay, this is 1256, 1256. Okay, so how we get this? We get from formula. We get from formula. Refer the appendix for the fixed end action. Fixed end action. Okay, always remember that fixed end action, fixed end moment, okay, or vertical reaction that we get from the appendix shows the behavior, shows the behavior. So so this is the right direction, this is the right direction because of the behavior, and we have to compare with the sign convention 3412. Then whichever opposite, so we put negative. So this is correct, negative number 2, because 2 for 2 it is opposite. So negative 12 at position 2. Okay, then we plus these two, we get equivalent nodal forces. Okay, we get okay, nodal forces, Q nodal forces, Q1 and 2. 1 and 2 means one is vertical force subjected at B, and another one is moment subjected at B. So please refer to the uh, unconstrained system 1 and 2, 1 and 2 here, 1 and 2 here. So 1 refers to 20, 20, and it is opposite. This 20 is opposite with sign convention here. So that is why we have to put negative. And moment is counterclockwise. Sign convention also counterclockwise. Sign convention also counterclockwise. So that is why it will be it is positive. So positive. So the rest this is the boundary between unconstrained and constrained. So the condition will be opposite. So known versus unknown. Known versus unknown. So this is correct. This is correct. Okay, Q naught. Okay, Q naught at position 2 is negative. So this is Q naught, correct answer. Okay, D1, D2, D1, D2, the unknown displacement. So this unknown displacement sometime is called as non-zero. This non-zero, sometimes non-zero displacement, sometimes non-zero degree of freedom. It refers to the same thing, unknown displacement. Okay, unknown displacement, non-zero displacement or non-zero degree of freedom. These two terms is also refers to unknown displacement. Unknown displacement, the boundary. Okay, unconstrained and constrained. So constrained means support, no movement. Support, no movement. However, there is a condition where the sum of the the value in constraint system is not zero. Okay, whenever there is a support settlement. So support settlement, when support settlement occur, when support settlement occur, so based on the given position, so some of the value, the zero value here will, okay, will have value, okay. So the stiffness equation, Q is equal to KD plus Q naught, like this. Okay, correct. So, and actually, whenever we solve, we only consider unconstrained system. So, the total, the equation in full like this is not necessary. Uh, it's not necessary. You don't have to write in full every time unless the question asks you to do so. Okay, but in order to calculate unknown displacement, you must have this. You must have the equation corresponding to unconstrained degree of freedom system. Okay, so means that this one is compulsory. Okay, this one is compulsory. This one is compulsory. Okay, in full depending on the question. Depending on the question. If there is a statement asking you to give the established stiffness equation, full stop, for the structure, establish stiffness equation, then you have to give established stiffness equation for the beam, for the structure, then you have to give in full. Okay, other than that, you don't have to give in full. It is just enough for you to write the equation in okay, in unconstrained degree of freedom system only, because when we solve this we get displacement, unless when we when the support settlement is given. Okay, so solve this using simultaneous equation. So okay, the answer D1 because it refers to vertical displacement, D2 refers to rotation. So this is actually delta at B, D2 actually theta at B. So that is why one is radian, another one is in meter. In meter. So for the unknown reaction, this is how we write uh, in short form, because in previous video I have shown to you the mathematical process of solving this. So this is how we write in short form. Okay, because we want four values of unknown reaction, 3Q3, 4, 5, 6, means we just need to consider this part. This part come from actually this. Okay, times with this, and we have to plus this to get this. Okay, either you want to write in short form and just give the answer right like this, or you want to write in mathematical form, doesn't matter. Okay, most important is the answer. Okay, most important is the answer. So this is Q3, 4, 5, 6. So careful. 4 and 6 refers to moment. 4 and 6 refers to moment. So we have to put the right unit. Okay. So here Amira, okay, actually have drawn the diagram, the shear force diagram. Okay, like this. Okay, the shear force and the bending moment diagram. Okay, we will check this later on. Okay, so next we have Iqbal here. Okay, So 3 nodes ABC, 2 do you have per nodes correct? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, correct, yeah? The label is correct. And then element number 1. Element number 1. Okay, make sure this value you must start with 2EI. 2EI. However, I want to check this. Okay. And 1, 2, 5, 6. Okay, and this is K. And don't forget to put EI. Okay, because this number cannot stand alone. Okay, it must pair with EI. So please don't forget to put EI. Okay, so okay, this is correct. This is also correct. Okay, this is how we calculate the equivalent element nodal forces. Equivalent element nodal forces. And normally we when we want to do this, we have to have the other one. Okay, the other one, so that it is easy for us to compare. So this is 3, 4, right? This is 1 and 2. So that when we can compare it very, very clear like this. Okay. So 2 is negative 12. So this is correct. This is 0. Okay. Either you want to draw two diagram or you just put the label, the sign convention like this. Okay, just below the diagram, the formula. Okay, so that you will not get confused. Okay, so this is in full the force displacement equation, or stiffness equation. Yeah, stiffness equation. EI 1, 2, 3, 4, 5, 6. Okay, D1, D2. Okay, Q naught. And then D value over EI. Okay, over EI if EI is not given. If EI is not given, then EI will be cancelled when you calculate the reaction. Yeah, the reaction. You get the same 48.165. 48 okay, 48.19. Okay, 67.4, 67.4, 7.8, 7.8, and negative 18. This is negative 17.998. Okay. Okay, same answer. Same answer. Okay, okay, next one. Muhammad Adib. Muhammad Adib. Muhammad Adib. Okay. So every time so always start with draw the label, the degree of freedom label separately, unconstrained and constrained. Okay, 1, 2 here, 3, 4, 5, 6. So the label 1, 3, 4, 5, 3, 4, 1, 2, correct. And another one is 1, 2, 5, 6. Don't forget to put EI. Okay, don't forget to put EI. Ni EI. Okay, so this is the structure stiffness matrix, 6 by 6 matrix. Okay, for Q, this is correct. For D, this is also correct. Okay, for equivalent element nodal forces, equivalent element nodal forces. Okay, 3, 3, 4, 1, 3, 4, 1, 2. 3, 4, 1, 2 3, 4, 1, 2. So, one negative at position 2. At position 2. So, this one. Okay, in full. Okay, this is the stiffness equation in full. This is due to unconstrained degree of freedom system only. So the answer over EI if EI is not given. If EI is given, then so you have to divide by EI for the answer in unit meter and radian. Then okay, substitute back. Okay, this is 1 over EI. Then only it cancel with this and this. 48, 67, 7.8, negative 17.98. Okay, next. Okay, next. Nazrul. Nazrul Okay. 1, 2. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. Okay. Six. Okay. Equivalent nodal forces. Stiffness equation for the beam. Okay. Stiffness equation for the beam. Okay. This is good, but you don't have to calculate it manually. Okay, because it will take your time. Okay, just use calculator. Okay, and just give the answer. Okay, 48, 67, 7.8, negative 17.98. Okay, so same answer same answer. Okay. Evilia. Okay. Okay, the label is correct. The label is correct. Okay, 3412, this is also correct. EI, you put EI here. For okay, Q. Okay, so this is nodal forces. This is nodal displacement. Okay, K2 K2 1256 1256 EI. Okay, K1 plus K2. This is equivalent element nodal forces. Equivalent element nodal forces. Okay, just sketch. 3, 4, 1, 2, 1, 2, so that you can compare the two, these two diagram. So we get negative at position 2 is correct. Okay, this is for element number 2, 1, 2, 5, 6. The label is correct. So we combine this. Okay, this is for equivalent nodal forces. Equivalent nodal forces. When we plus this, we get, okay, this is correct. Okay, so the stiffness equation, so this equation, okay, you must be able to imagine this all the time, but you don't have to write in full all the time. Okay, so EI ada sini EI, so this is correct, this is correct, this is correct. Then due to unconstrained system, 1, 2 only, because there are two degree of freedom in unconstrained system. Okay, solve using calculator directly, so we have extra time. Okay, so the unit, okay, D1, 1 and 2, remember 1 and 2, this is 1, this is 2. So D1 should be in meter. Okay, 1 is vertical displacement. D1 is vertical displacement at B. D2 is theta at B. Okay. So Q times D. Okay, plus 3, 4, 5, 6. So 48, 67, 7.8, negative 18. Okay. Correct. Okay. So from this, the answer. Okay, the question, this is the question. So now, okay, so we are going to draw the diagram together, the shear force diagram and bending moment diagram together. Okay, the beam first. Okay, the beam. Okay, 4 meter, right? Point load at the center, and it is this is 20, right? 20, and moment is 40. UDL 9, 9. UDL is 9 kilonewton per meter. 4 meter. 4 meter, this is also 4 meter. Okay. So 3, Q3, Q3. Because this is 3, 4, right? This is 5, 6. 3, 3, 4, 5, 6, right? So means 3, 4 is Q3, Q3. So Q3, Q3 is 48.17, 48.17. Q3, it is okay, this one, this is 48.17. This is 48.17. The moment means Q4. So Q4 is 67. 67 positive. What does it mean? It is counterclockwise. Okay, counterclockwise. We follow the sign convention. This is 67. Okay, positive means same with sign convention. Negative means opposite with sign convention. So 67, 67 point, okay, point 48. Okay, point 48, 48. Then Q5, Q5. Q5 is Q5, 7.8, 7.84. Okay, this is 7.84, 7.84. And Q6, Q6 is negative. Okay, negative 18.04. Negative 18.04. Negative means opposite with sign convention. Opposite. Sign convention is counterclockwise. Counterclockwise. So negative means clockwise. Clockwise. So this is 18.04. 18.04. 18.04. Okay. Okay. So for the diagram, okay, I just draw the grid line first. Okay, assume that this is equal 4 meter, 4 meter. Okay, so the shear force diagram, for the shear force diagram, we just need to focus on the shear value. Okay, the shear value. Okay, it is 48.17. Okay, diagram, either it is shear force diagram or bending moment diagram. We must understand that it is, it start from zero, it start from zero and at zero. Start from zero and at zero means the first point is zero. The first point. Okay, so the first point here is zero. And the last point also zero and at zero. Start from zero and at zero. That's the concept of diagram. Because the system is in equilibrium, right? That is why. Okay, it must close loop. Close loop. So the first point is not 48.17, but the first point is zero. Zero we plus with 48.17. Okay, zero, zero, we plus with 48.17. Then we get the second value. What is the value? It is 48.17 as the second value. So this is 48.17. Okay, after that, because of UDL, we have to minus, right? 48.17 minus 9 minus 9 times 4, 36. Minus 36. Minus 36. Okay, so it is 48.17 minus 36. It is 12.17. So still positive value, right? So let's say this is the point. Okay, let's say this is the point. So this is 12.17. 12.17. Okay, 12.17. Then we meet this 20. this 20, means that 12.17 we have to minus because it shows the downward direction, the 20. Okay, so we minus by 20. So it is a negative 7.83. 7, this is 7.83. Okay, 7.83. And now no more. Okay, means it must go straight until it meet this point, 7.84. Okay, so look similar, right? Okay, so the point is here, 7.8, 7.83. Okay, 7.83, 7.83. Then look at the arrow. The arrow, okay, shows that it is going to close the loop, end at 0, end at 0. So this is 0, zero, right? This is 0, right? So the last position is 0. Last position is 0. Start at 0, end at 0. Then, okay, we will join all this dot. Okay, this and this, and then this. Okay, this one goes straight. Okay, and then, okay, so this is positive, this is negative, and this is shear force diagram. Shear force diagram. Okay, 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 and after that, after shear force diagram, we will draw bending moment diagram from shear force diagram. From shear force diagram, we will calculate bending moment. From shear force diagram, we will calculate bending moment because shear force diagram, shear force, the unit is in kilonewton. Shear force. Shear force, the unit is in kilonewton. Okay, when we consider the area, it is kilonewton times the length meter. So we get kilonewton meter. Okay, shear force, all unit in shear force diagram is in kilonewton. Kilonewton, shear force. Okay, and 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 if we calculate the area of shear force diagram, it is kilonewton and meter. Kilonewton and meter. So we get kilonewton meter. And kilonewton meter is the moment. Moment is in kilonewton meter. Okay? So we continue to draw bending moment diagram. Okay? Bending moment diagram. So we will concentrate on the moment, the moment value in the diagram. Okay? Same as shear force diagram, the diagram, the bending moment diagram also start at 0 and at 0. Start at 0 and at 0. Okay? Means the first point in the diagram is this 0 point here. And okay, the last point in the bending moment diagram is also 0. Okay? 0. First and last point. Start from 0 and at 0. Okay. So look at the value. the moment value at A. The moment value at A is negative. It is counterclockwise. And now when we draw diagram, we will go back to the concept of direction. Counterclockwise is negative. Clockwise is positive when we draw the diagram. Okay, so this is counterclockwise. And for bending moment diagram, for design purpose, uh, normally we draw negative upward, okay, above line. However, for analysis, okay, for analysis, doesn't matter. We can draw positive upper line, negative below line. Doesn't matter. But for design purpose, so when you take RC design, okay, when you want to draw, you will use this bending moment diagram, and at that time, you have to draw negative upward, okay, because okay, crack pattern we identify from the bending moment diagram. Okay, so here, so it is negative, it is counterclockwise. This is negative 67, negative 67.48, negative. Okay, doesn't matter if you want to assume negative above line or positive above line, but you have to label which is negative, which is positive. Okay, so I want to put below line negative, positive, uh, above line negative, below line. Okay, it is negative, means that 0 plus negative, 0 plus negative, so we get negative 67.48. So it is this 67.48, 67.48. Okay, and in diagram you don't have to put negative, cannot. Okay, just put the value. Okay, 67.48, the second value, not the first value, because the first value is 0. 0 is the first value. So 0 plus negative 67.448. Okay, for 0.48. Okay, next point, because it is trapezium, there is no intersection in shear force diagram. Remember the bending moment diagram has maximum moment whenever the shear force diagram has intersection, cross. Okay, but this time we get trapezium, so there's no intersection, means there's no maximum moment. Okay, intersection like this means there is a maximum moment intersection. But now there is no intersection, it is trapezium, so it is just curve line. Okay, this 67.48 is negative, negative 67.48, negative. What we need to do after this is we have to find the area of the trapezium to get the next value at point at B. Okay, so it is negative 67.48. We have to plus the area. Why we plus? Because it is positive shear force diagram. So it is negative, start with negative 67.48. It is negative, right? Then we plus by the area of shear force diagram. Okay, the area. Okay, we calculate the area first. Okay, area of shear force diagram, it is 48.17 plus 12.17. Okay, times with 4 meter, divide by 2, right? The area. So the area is 120, 120.68. Okay, 120.68. So the previous value is negative 67.45. 67.45. 48. Negative 67.48. So what we get is 53.2 and it is positive. 50, this is 52 and 53.2. Okay, so it is negative 67.48. It is negative 67.48. We have to plus the area of trapezium and we get positive 53.2. Okay, then we continue from 53 point. No. We have moment. Okay, we have moment at B. Okay, the moment is 40. The moment is 40. Okay, if there is no moment, we just continue to minus the area of BC, but it has now 40 kilonewton moment, and it is counterclockwise. It is negative. So 53.2 that we get, we have to minus 40 first. So we minus 40, so we get 13.2. 13. So we get another point here. It is 13.2. After we minus by 40. Still above line. 13.2 positive value. Okay, then only we minus by the area. Okay, so 13.2 we have to minus the area of rectangular. The area of rectangle, it is 7.83 times 4. The area times 4. So what we get is negative. It is negative side 18.12 negative, and this negative 18.12 is not the last value, because the last value is 0. 0 is the last value. Means that this 18.12 we have to refer back to diagram. Look at the value of the last moment at C. It is 18, 18.12, and then we now see the moment value here. It is positive direction, right? It is clockwise. It is 18.04. 18. So assume 18 lah, 18.0. Okay, so 18. So when this 18 we plus by this. Okay, plus this 18. So then we get back to 0. Okay, so assume 18. Okay, normally more decimal places you consider, you will get accurate one, but however this is correct. Don't worry about the 0.0 something that you get. Don't worry. Okay, so the concept is there. So it is 18 negative. 18 negative. Go back to the diagram. Look at the moment direction and the value. It is positive 18. Okay, here is negative 18. We have to plus with the last moment is positive 18. So that's why we get back to 0 value. Okay, 0 value. Okay, then we draw the the diagram. Okay, so okay, for A, this is B, B, okay, C, C, this is straight line. Okay, but AB because of UDL. AB is UDL kan? Okay, AB is UDL, so this one we get, okay, curve line. Okay, wait. This one. Okay. Okay. So this is positive. This is negative. Okay. The first value, the second value, this is the third value. Okay. Number 4 value, number 5 value, last value. Okay. First one, first, 2, 3, 4 value, value number 4, value number 5, value number 6. So that's the flow. That's the flow. So we get back to 0. Okay. So that's how we draw the bending moment diagram, shear force diagram and bending moment diagram. This is BMD. Okay, bending moment diagram we get from shear force diagram, the area of shear force diagram. Okay. So after uh, we have analyzed the beam using stiffness method. Okay, the value that we get, the reaction that we get from the analysis, okay, we put into the diagram in full like this. Okay, so and of course the system must be in equilibrium. So you can check a total F1, total Fx as usual, total moment as well. Okay, then when it is in equilibrium, we can start draw shear force diagram and bending moment diagram. Okay, like this. So this is how we draw the bending moment, the shear force diagram and the bending moment diagram. Okay, so this is correct. Okay, so hope you understand about beam analysis using stiffness method. Okay, so next video we will focus on the effect. The effect, number one, it is support settlement effect in beam. In truss also can, because it is the same. So I will do one beam question considering support settlement, and I will also produce another video discuss about the effect of temperature changes and fabrication error in truss as well. Okay, I will let you know when is the session, and after that we will continue to frame. Okay, so if we can finish this earlier, we will start MDM earlier, so that we do not have to wait until until week 10. Week 10 week I think we can start at week 9 or 10 to start the MDM as preparation for test. So that after test will be in week 13, yeah, in week 13, test in week 13. Okay. So that after that we will have another session, another week to refresh back the stiffness method and flexibility method before final exam. Okay. Okay, that's all for this session. Thank you very much. Thank you for joining. Okay, hope you get something from this session. Okay, continue to submit, eh? Submit and exercise, submit. Okay, I will return it back to you. Okay, the one that I have commented. Okay, I will put in one folder and you can take yours lah. Okay, for your reference. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.